If you get smacked in the head by a ball, the reason the ball is moving in the first place and so able to put that force on your head is that the ball carries energy. We say the ball has kinetic or movement energy. But energy in itself is really difficult to imagine or picture in your mind. Like, if I say that I don't want you to picture the ball, but I want you to picture the energy that just happens to be being carried by the ball. That's a difficult ask. Probably the most helpful way of thinking about it is that energy is a kind of invisible fluid that things can carry. Really loud sounds can physically hurt your ears. The air molecules next to your eardrums are vibrating really hard because these air molecules are carrying a lot of energy. If we ask you to imagine the energy itself, not the air molecules, then again, it's probably as good as you can do to think of an invisible sort of fluid. The same with the heat energy in a hot pan. If you're trying to think of the energy itself, not the molecules that make up the metal of the pan which carry it, again, it's probably as good as you can do to think of the energy as an invisible sort of fluid. Moving electrons, which are way too small to see, also carry energy. Loads of moving electrons make up electricity, which is where the name comes from. Don't be overthinking the fact that electrons are doing the carrying. Electrical energy is just another form of energy. The electrons are moving, but they are carrying an invisible sort of fluid. This electrical energy can be used to light a bulb from the heat in the filament, or it can be used to spin a motor, or it can be used to turn something else on. The common circuit symbols are in another video, and you need to know them. The reason that these electrons can move in the first place, and so carry this energy, remember, is that electrons have this thing called negative charge. Charge is a bit like magnetism, but it needs an electric field, not a magnetic field, to make it go anywhere. This is what the electric field that moves electrons looks like. And there's the electric field from an individual electron. But never mind all that. The electrical current flowing through something means how much of this charge is moving past a point each second. It's because of this charge that electrons carry energy. So more charge delivered each second means more electrical energy delivered each second. If you touch a circuit with a high current flow, in other words, a large amount of charge delivered each second, there will be so much electrical energy delivered to you each second that you will get a bad shock. This idea, that electrical current is the quantity of charge delivered each second, leads to a formula. Electrical current equals quantity of charge delivered divided by time. The SQA, being the SQA, rearrange this formula to make quantity of charge the first bit. So now, quantity of charge that has been delivered equals the electric current times the length of time that current has been flowing for. So on the formula sheet, quantity of charge, capital Q, measured in coulombs, capital C, is current, capital I, measured in amps, capital A, multiplied by time, which of course is in seconds. The units of charge, coulombs, come from the name of a French physicist. And the reason that current is shortened to capital I is that the word for current in French is intensity, which sort of makes sense. The current of a river could be thought of as the intensity of the river. Anyway, people find this equation tricky, so have a good look at it. If your mind is a bit minced already, just use the formula as a basic device for churning the numbers out, and don't think too hard about the backstory. I've only gone through the backstory with you here, so you're not just being asked to use letters and words that feel random and confusing and unexplained. But you'll never have to explain the story yourself, so just watch this video a few times until you feel the concept makes sense. But don't worry about remembering. The only thing you have to be able to do is use that formula. Here's a worked example using this formula. What would you do with it? Come on, read it. Then what would you do? Shopping list. Don't forget to deal with time. Formula. Numbers in. Final answer gets units. Do you remember us talking about the electric force field? The strength of that force field is called voltage. So voltage pushes electric current round a circuit against resistance. Now, as the slide title suggests, there is a formula linking these guys, but we'll come back to the formula later. For now, voltage pushes current round a circuit against resistance. The word circuit means a circle. Electrical energy needs a complete circle, a complete circuit, to move around. Anyway, sources of voltage include batteries, the mains, solar panels, and a few other things. Here's a circuit where the components are in series, one after another, like a TV series, But more importantly, they are all in a single loop. This means that if there is a break in the circuit, electric current stops flowing, and everything stops working. This is, of course, why switches are always put in series with what they are needing to turn off and on. When you plug multiple things into a mains socket, the circuits are separate. They are called parallel circuits. The important thing is that they are separate circuits. They just happen to share a voltage source. The way circuit diagrams are drawn for parallel circuits, I think doesn't make it clear enough that the circuits are separate. But they are. And if one circuit stops working for whatever reason, the other circuit stays working. This is why pretty much every circuit in your house is a parallel circuit. You don't want your lights to stop working just because Grandpa has microwaved a plate of food with the metal cutlery on it and blown the damn thing up again. With the separate parallel circuits, the only thing the circuits have in common is that they happen to be connected to the same voltage source. So each circuit gets the same voltage supply, which is equal to the voltage of the battery, or the mains. The total current that shared voltage source is making happen is the current through each of the attached circuits, added together. With mains sockets, when the total current that the mains socket is making happen gets too high, the socket itself can get an electrical burn, or even the leads start to melt. Hopefully the fuse burns out before the heat gets any worse. Some people like an analogy, so here's one. If you go to Tesco's supermarket, the total customer current going out through the front door is the customer current through each checkout, added up. Whether or not you like the analogy, look at the numbers in the circuit shown. Also with parallel circuits, as each separate circuit has its own connection to the battery, each circuit gets the same full blast of voltage from the battery. The analogy at Tesco's could be that each checkout has a checkout assistant who has been equally trained to push customers through their checkout. With a series circuit, think of a mains water pipe with partial blockages in it. The more blockages, the slower the current, but equally that slowed current has the same value right along the pipe. Also making sense with a water pipe analogy is voltage push in a series circuit. As there is only one pipe, that voltage push down the pipe is shared out between blockages. The bigger an individual blockage, the more water pressure builds up behind it. And with a circuit, the bigger an individual component's resistance, the bigger the share of the voltage push it ends up getting.